Sure, thank you. First, thank you, Christo, for inviting esteemed colleagues and guests. Today we're gonna talk about Synth. It's an AI-driven materials discovery platform. So think about accelerates research by predicting new molecular combinations by intended properties instead of composition. So the agenda today, we're gonna go over introduction, the problem statement, why I created it. We're gonna go over how it generates materials and analysis, as well as the peer-reviewed and machine learning libraries that are used in the early predictions and generation of candidates. And then we'll talk about why we use GPT-5 and the deep reasoning. We'll do a quick demo, talk about the team, a little summary, leave room for questions at the end. And if I talk a little fast, you can slow down, just let me know.
Slow down.
Well done.
A little bit about myself. I have background in philosophy, software engineering, military intelligence, DevOps, tech startups, international investments, and telecom. At an early start of development, I started building code and then IBM 2000 on QBasic, if anybody remembers those. And I was building enterprise websites by 14. In military intelligence, I developed some software to process satellite feeds and enhance mission targeting. And then in leadership, I developed a good majority of AT&T's machine learning platform services, and then ended up leading the DevOps for all technology. I built global teams and launched global products, PwC, and I founded a DevOps school where I trained and placed over 100 engineers in the industry. Current role in my day job, I'm Senior Director of DevOps, Chairman and President of YourTel Inc. We're a telecom company focused on acquisitions in Africa. And then the CEO of Zuko Investment Groups of projects in sustainable agriculture, oil and gas, renewable energy in Africa. And then in the US, I have retail, restaurants, and tech startups. And so Synth really came about because I was developing a graphene concrete battery for my telecom project. And I wanted to create new materials or predict new materials that might help what I was doing. So I kind of created Synth to help with that, and I realized it could be used kind of in a broader way. And so really the vision is to accelerate material innovation by integrating peer-reviewed scientific libraries to start with known behaviors, machine learning, and then GPT-5 to use interdisciplinary reasoning over physics, chemistry, and material science. So no one person can hold all the knowledge in their head. So leveraging GPT-5's ability to reason on advanced science at a 98 to 99% accuracy level, we're going to combine the corpus of scientific knowledge it's trained on to analyze what we predicted from the peer-reviewed libraries. And the goal is to essentially drastically shorten the path of theoretical to practical. Because the problem, traditionally, discovering new materials, conductors, energy storage, high strength alloys or catalysts, it's slow and it's essentially just trial and error. You generally start with a composition, a known structure, and then you simulate it or synthesize it, and then hope that it reaches the target properties. And a lot of times it doesn't. So traditional time it takes to generate new materials about 10 to 30 years, and it can cost anywhere from 200K to 1.2 million. Synth reduces this time by a factor of 3 to 10. So what if we could change it? That's why we created Synth. It was essentially to flip the workflow and start with the properties we want. So instead of creating a composition that might have the properties, we want to define the properties we want from the material and then use open source libraries that are based on peer-reviewed science to create candidates, and then GPT-5 to analyze those candidates to give you a starting point. Doesn't mean it's going to be correct or 100% accurate all the time, but it's smarter and more accurate than humans. So it gives you a really good interdisciplinary start to understand which targeted molecules and compounds you want to create before you ever go to the lab. So it reduces the trial and error time by 80 to 95%. And so the overall development cycle and cost should be reduced about 3 to 10x using Synth, because you're starting with the properties you want. You don't have to come up with composition. It does that for you, and then it predicts and gets smarter over time. So the more people that use it, the longer it runs, the smarter and better it gets at predicting. So how it works. We have a nifty little flow logic diagram on the left here, but it starts with property specification. Things like, I want a room temperature superconductor that's chemically stable. The platform then takes that property and generates candidates and then uses prediction libraries to predict the properties those candidates will have. And the property prediction uses libraries like PyMatGen, MapMiner, SGBlib, and ASE, which are scientific libraries trained on the materials project, which is an open source materials project, to predict how crystal structures and atomistic formulations will happen. And then we use XGBoost and LightGBM to do the machine learning, which takes scientific data, converts it into numbers, and then learns over time to make smarter. So every time we predict 100 candidates, we can learn and then get smarter every time we do prediction. And then we use GPT-5 for the reasoning, right? GPT-5 just came out, but it's trained on virtually the entire corpus of scientific knowledge that's published. And it has a 98 to 99% accuracy when using the reasoning function at an expert level of all disciplines. So we train across physics, chemistry and material science to analyze the predictions we made, to understand like what properties it has, how to make it, what safety considerations you have, and understand, and it has all the sources and theoretical assumptions that it used in making those predictions, and a confidence level of how accurate it thinks it is and how likely it is to synthesize. And then we create 2D and 3D model simulations. So we do 3D video simulations of molecular bonding and the predictions. We do 3D interactive molecule models, so you can like turn it and look at how it should form. And then we also do molecular diagrams, structure diagrams, classical chemical structure diagrams, and an Ehull diagram, which essentially shows the thermodynamic stability of the molecule they're trying to make. And then the continuous learning and retraining, every 100 candidates it produces, it gets smarter. And then later on, when you go in the lab, you try to make these materials, you go and put those results back in, and it's gonna get smarter. So was my prediction right? Was the outcome correct? And you put those results back in, and then it retrains itself to get smarter. And over time, if you have a distributed network of scientists and universities using this to predict and make new materials, it's gonna get infinitely smarter over time. Again, the peer review library. So IMAGene, it essentially is a tool for structure manipulation and symmetry standardization. SPG, I can't speak today. It essentially determines the crystals Bravus, Lenus, and space group and point group, and standardizes structures into conventional or primitive cells. So these two libraries combined with AOC and MapMiner are used to generate the candidates and predictive properties. And these are all based on the Open Materials Project and peer-reviewed science. So nothing's a guess here. It's all based on science that we start with. And then we use machine learning libraries like scikit-learn, XGBoost, and IGBM. And those are essentially used to turn our predictions into a set of numbers that the model can then learn and understand if its prediction was correct or not. And it'll just keep retraining itself and get smarter over time because it understands how the numbers change, and it uses math essentially to model the changes in the structure of the scientific data it produces. We use RDKit for the diagrams, so it's a library that used for like molecular representation analysis and visualizing molecules and atoms. And then OpenAI is again used for the analysis on the back end. These slides will be sent out too, and there's some more explanation down at the bottom, like what machine learning models are being used and why. And the GPT-5 expert analysis is essentially expert level reasoning, right? Because like no one person can know chemistry entirely, physics entirely, material science entirely, and all the scientific data that's been published. Like we're just not that smart, right? And while it does make errors, so do humans, right? So it's not something that you rely on, it's something that you use as a starting point. Like this is what it should be. This gives me a good idea of what maybe it could be. And so that structured reasoning essentially is analyzes the complex variables like atomic composition and band gap dependencies. Stuff way smarter than me. Now we use diagrams to visualize. A lot of people are visual. Having just data or reading data, seeing equations doesn't really help sometimes. So we create a series of diagrams that kind of cover the 3D simulation of the molecular bonding, interactive 3D model, the convex Hull stability analyzer, which essentially is the Ehull's thermodynamic stability, like how accurate is this going to synthesize? Like, is it possible? Is it a material that makes sense? We have an electronic structure diagram that's coming soon. I'm still working on that one. Chemical structure diagrams, molecular diagrams, really just helps you visualize what you're doing. Now it's really performant too. So like projects, the only other projects that exist like this really are like the Microsoft one and the Google one. They're run on supercomputers, right? Not everybody has access to supercomputers. Currently, the project's running on 2 CPUs and 2 gigabytes of memory, and it can produce 1,000 candidates in 20 minutes. So you don't need access to multi-million-dollar supercomputers to use Synth. And that's kind of the point. So we can do distributed prediction and then feed the information back into the system. So we don't need giant supercomputers to do material prediction. It's not isolated to a few groups of disparate rich people. Anybody can use it to predict materials. And it can scale horizontally. So the more users or the more predictions that are being run, it'll scale horizontally. It's fully automated. So you don't have to worry about like, oh, I gotta go get a big machine. It just fully scales automatically based on the number of users that are using it. So roadmap. So what are we gonna add to it, right? We're gonna expand the simulation suite, increase more visualizations. I need to interface with some more domain experts. Get some people on the project that can help me understand what simulations would be more useful to chemists, what simulations would be more useful to physicists, material scientists. We're gonna find the synth generation, essentially the crystallographic and structural files. We need to improve them to make them a little more accurate. These are materials that don't exist, right? So you're essentially guessing on what those structures are gonna look like based on the science that we have. And I'm pretty sure they can be refined because I'm not a chemist. This is, and we do results driven learning, I mentioned that. So when we go make the material in the lab, I want them to feed that information back in the system so that it can understand whether it was right or wrong. And over time, again, it's just gonna get smarter. Right now, it generates a PDF, but I wanna change that into an automatic latex publication. So basically produce a publication-ready academic paper. Once you've analyzed it, tried to make it in the lab and fed the information back in, click a button, it'll produce a fully made academic paper for you with sources and everything. So now we're getting to the demo, the fun part, which y'all can hear see. So when you go to the website here, you can click log in. It is still open. I'll show you. So it's still open. You just go to sign up, put in the name. Once you sign up, you need two things. You need an open materials project API key, which is free, and a GPT-5 key, which you would have to charge with money. It's not super expensive. It's about $1 per analysis. So you come in, it's gonna ask you for those things. It's gonna ask you for the open API key and the materials project key. That's used because on the back end, it's making an advanced series of agentic queries to OpenAI to analyze the material. You can't just say, give it one information, one query and say analyze it. It just won't give you that data. So we make a lot of queries on the back end to GPT over different questions like, what's the quantum properties look like? What's the electronic structure look like? Okay, what applications in commercial industry can use this for? How do I make it? Right? And it gives you a step-by-step analysis on how the material's made. So I'm not gonna fill it out, I'll just log out and log into an account, but you guys can sign up and put that in and just use it right now. No questions asked. If you wanna play around with it, please feel free. Just note that I'm making changes daily. So if it breaks for a second, it'll be fixed in a few minutes. This is what it looks like. So say you're in, you put your keys in, what do you do then? You come over here to material generation, then you go, I wanna start autonomous learning. So here's where you define your properties, right? You can type whatever you want in the box, or you can use these quick properties here. So if you wanna give me feedback on what properties make more sense, and to add, I can add those quick properties as well. But say I want a room temperature superconductor that's chemically stable. When you click generate ranges, it takes all the properties that PyMatGen and MapMiner can predict, and it feeds those into GPT and it says, I want these properties. What are the ranges that make sense for predicting materials for these properties? And you can tweak them. It just gives you a starting point so you don't have to fill out all the boxes yourself. So you're gonna see in a second, it's gonna populate a series of boxes and all the properties that it can predict for material. And you could then go in and tweak, like I want the temperature for superconducting to be within this range, right? I want the conductivity or the band gap to be within these ranges. So you can edit these all you want, but it's just a way to get you started so you don't have to type every box out. And then if you click start run, it starts a background process that automatically starts predicting materials, and you can see the progress here. The generated materials and the prediction process and the learning process. So this one's gone through 23 cycles of learning. It's generated 2,100 materials, and the properties it's predicted are 2540. These numbers don't match because I've reset the database a few times on a few things, fixing it. And then once it produces them, it color codes them, right? So it's gonna color code them green, yellow, red. Green means the Ehull, which is the thermodynamic stability, is less than negative 0.2, which means it's likely to be able to be made. When it's yellow, it's less than 0.5. You might be able to be made. And when it's red, it probably won't synthesize, but you can try. So let's just filter by green for now. So we'll filter by green, it's gonna take out all the other ones. And then let's go look at one we've analyzed before. So we have KRMG6. It comes up with a systemic name, common name, molecular name. Now this is a material that's never made, right? It's completely new. So it comes up with what it thinks it should be, and it probably will change. It creates the molecular diagrams, the structure diagrams, the classical chemical structure diagram, and you can see it's off, right? It doesn't show all the bonding lines because the synth file that's being generated on the back end needs to be improved because it's new material and it just didn't make it correctly. So refining that process still needs to be done. Then it does the Ehull diagram. And then you have our 3D model. I need to add labels so it makes more sense, but the structure's in place to generate this 3D model. So you can see this one doesn't have the bonding. So again, just like in our classical structure diagram, these are used by those crystal structure files that get created for an unknown material. So that process has to be refined, and I'm not a chemist, so I need to work with some more chemists to refine the process generation to make it better.
Or shouldn't there be 6 magnesium?
There should, yes, but the CIF file will generate it wrong, that's the point. That's what I need to refine. And then we have the 3D simulation. You can see only one of the bonding lines played. So again, this is also based on that ZIP file. So if I refine that ZIP file, all these will be correct and accurate. Sometimes it's 100% accurate, sometimes it's not. And so it just depends on if it generated an accurate one for you or not, and refining that process shouldn't take very long, but I've been fixing other bugs recently. Then it goes into an overview of the material analysis. You have key features and potential applications at a high level, as well as the primary class and conductivity and mechanical. We're not gonna read through it all, it'll take way too long, we don't have that much time. And then it goes to essentially a theoretical analysis from chemistry, physics, and material science. It goes through quantum foundations, thermodynamic landscape, uses all the equations that it uses to make these. At the bottom, it shows you its assumptions and sources it used to make the analysis as well. Structure property links, and then goes into material identification, primary class, conductivity, mechanical density, and the nomenclature. And then we go into key features and properties. So all this is what GPT is doing. This is the analysis it's doing on those predicted properties. And so you have optical properties, photons, mechanical performance, thermostability, drive calculations, practical implications. Then it goes into a deeper material analysis and description. And then we go to potential applications, what it can potentially be used for based on its properties. We go in the materials table, basically everything you're gonna need to make it.
Could you roll back?
Yeah,
a
go ahead.
bit?
Which one?
So what it could be used for, I can't read the text from here, so it's an example of what it could be used for.
Yeah, so, this one, it says it has a high static permittivity, candidate for high K dielectric, in the extreme band gap electronics, capacitors, dielectrics, a gate polymer embedded with nano dielectric, so. This one is high K dielectric, based on its properties, right, so. It's a potential for superconducting at cryogenic temperatures under ambient pressure, short version, so that's what the property was I used to predict it, right? This one does it at 8K though, so it's not room temperature. But 8K is still cryogenic temperature, so you can use, I think, liquid nitrogen for that, or maybe helium, I don't remember, but.
So could you enter, variable temperature, like, because sometimes when you're applying something, it can be super hot, and then it makes the material that you're applying it to in a 3D printing situation warmer. So can you have variability, or does it have to be static?
You can have variability, it'll actually predict the variability in behavior under different temperatures as well for you. And you can tell it like whatever properties you want, if you want variable temperature, like at different like densities or different behaviors, you can describe that in the properties and it'll put the ranges that'll give you that. Essentially, this one is a low temperature superconductor. That you can use at cryogenic temperatures, you don't have to get to 0 Kelvin to make it work. It goes into materials cable. Safety considerations, like if you're going to make this in a lab, like what should you consider is dangerous about making this material? And then it gives you a step-by-step synthesis procedure, on how it could theoretically be made. So like what steps do you have to do in the lab? How do you have to make it? What measures of each thing do you have to use to try to put this thing together? Right, because like otherwise you'd have to go do the research, figure that out, and take you a while. It's a theoretical material, so you might not know how to do it. So it goes through the full steps of how to do that. And then it gives you quality control, so like, what do you have to consider when making it to make sure that it's gonna be of quality, it's gonna produce what you want? Then we go into the full electronic structure analysis, with all the equations used to do it. Then we go into the quantum transport property, so it's not just like analyzing and telling you what it's gonna do, it's showing you the math behind why it thinks it's gonna do that. Based on the values that it predicted. Thermodynamic stability studies. Crystal structure prediction. And then we go into safety environment considerations. Environmental impact, storage, disposal, and then it goes into further comprehensive prediction analysis on like what its properties are gonna be. Mechanical, thermal, optical, magnetic, and stability. Then it goes further into property correlations and relationships, as well as prediction confidence and uncertainty. So again, it's trying to tell you how confident it is in itself to be able to tell you what this is what it's gonna actually do.
I'm wondering, did you ever have a situation where you told the system to ignore everything after a certain date and try and simulate the discovery of a substance that's been in, say, the last 5 years? Say, oh, cut it off at 2020.
Yeah.
And then predict this material that we've got in 2024.
I haven't tried that. That is a good test. I'm really gonna try that. I'm gonna build into the system. That's a really good test to understand if it can
Well,
accurately.
just a simulation of the actual discovery.
Yeah,
And see what it came up with, what the traditional method.
That's a really great input. I'm gonna actually put that in tonight, cause I wanna see if it's accurate. That's a good idea. I never even thought about test that way. Thank you. I know I haven't done that yet, but it can be added pretty easily based on how it's set up. Then again, it gives you like the theoretical methods and assumptions it used to make those predictions and analysis. And it goes further into like industrial applications and use cases. Yeah, and it shows you the math, like, so basically, thermoelectric materials, battery anodes, and how it can be used in like a commercial industrial application. And then we go to comprehensive prediction analysis. There's still some things that haven't been determined on this one, so I'm still working out these ones right here. But it goes in and fills out what it can for now, into a full prediction table. So some of the data just isn't there yet. I have to add it for the analysis.
Did I understand you correctly? So it's got a 95 to 98%.
Yeah, so GPT-5 in its analysis currently at the measured rates has a 98 to 99% accuracy on advanced scientific inquiry at an expert level.
And so are you measuring for this particular application?
That's when someone makes it and feeds the data back in, that's when it'll measure that.
How do they feed the data back in?
Yeah.
You wait till they publish the paper in Science and then you feed the science article in, or?
No, they're using the system, so they would just go put the input values of what it actually was into the system, and it doesn't get shown to anybody, it just feeds back to the system for learning.
And that's via the API.
Yes, yeah, it'll be a modally pop up, you just put in the data. And you can even write and describe the behavior too, it doesn't have to be just numbers, and then that'll get fed back in and then reanalyzed and retrained. Because what I'll do is I'll take that description plus the numbers, feed that into GPT, give it what GPT gave us, tell it to analyze the difference and feed that back into the model in the vector format essentially. So again, it goes through all the data, shows you all the math used. It analyzes a bunch of stuff, we're not gonna go over that, we're running out of time. And then it gives you the sources it used to do it. The actual academic sources you can go look at. There's probably some it missed, so we can refine that a little more. And then the initial predictions are right here. So the initial properties that it actually predicted that generated ranges that you put in at the beginning, and it gives you a confidence value, how confident it is that those predictions are correct. And then,
What's the red one? I can't read it from here.
Young's modulus.
And so what is that telling you as the user of, okay, how many greens were there when you?
2. But those 90%, the rest are 70%.
So it's
No, I'm sorry, when you were originally generated and they say you got greens, you got yellows, let's just look at the greens.
Yeah.
How many greens in this particular?
Okay, so
Is it hundreds or?
the only green thing that is actually being filtered by is the Ehull, which is the thermodynamic stability. So when you filter on the list, it's telling you the ones, like when you filter by green, is it gonna be stable if I try to make it, essentially? Short
So
version.
that's what you used on the front end to get this list of greens, and then you randomly went and selected one, and that's what you're showing up?
Yes,
And then this red is telling you something about the viability of that.
yeah, whether it's confident on that particular property, if it's gonna be correct or not. So it doesn't know how to actually predict that one, basically. 'Cause it doesn't know from the formulation, it's a new material, right? It has no, using PyMagin, open materials project has no idea what that behavior is gonna be, essentially. The other ones, it's pretty confident, 70% is pretty high. It's pretty confident the band gap in the Ehull, right? And then here it goes into how it calculates those as well.
So it's quite a leap because this material doesn't exist.
Yeah.
To think that its confidence is
Yeah,
accurate.
And then
It's a huge leap.
and it gets smarter, and the more information we feed it, the more accurate it'll get it predicted, because it'll have that information. Now, I tried to make this material, and then essentially what it does is it just converts it into a vector series of numbers, that's how machine learning works. So when we feed that back in, it'll just start comparing those lattices of vectors and start getting smarter. Not even just based on specific materials, but just like based on everything it predicted, you turn it into numbers, you feed it back in, and it just starts measuring the difference in numbers between the data and gets smarter over time.
Is there some comprehensive reporting of how well it's doing?
Not yet.
Because there's a lot of moving parts and there's a lot of bell curves in here for error bars.
Absolutely.
And you combine them all together and, you know, the science would tell you that your end results can be,
Yeah.
Right.
right? So it'd be really good to know, is it getting smarter? Is it getting better?
Absolutely.
I love the test you dreamed up.
Yeah.
I was thinking of, you know, can we start making lots of materials so that we can start seeing how good this thing is? But if you don't know how good it is and not how Not sure how valuable it is.
Well, it's a starting point, right? It's not 100% accurate. So instead of you trying to figure out a composition that might work and do trial and error, it's trying to figure out compositions for you that could work.
Yeah, but not all problems converge.
That's true. 100% true.
This one feels like it might not.
Yeah, well, that's why the system's created to take the feedback, right? Because someone has to go make the material and feed the information so that it knows where it made mistakes. So we'll show you how like they're actually analyzed. So when you start a material that hasn't been analyzed, it's only gonna show you like, not that one, like this one. So we come down, like, there's nothing here, right? It's just gonna show you the properties. So you have to click analyze, and that's gonna go make the series of queries based on the properties. Like, I'm gonna give you these properties set. I want you to look at the entire corpus of scientific knowledge for chemistry. Analyze it based on that. Physics, analyze it based on that. Material science, and then it tries to predict it based on the properties you're giving it and the information you're giving it, and it's always feeding the information predicted previously back into the system. So as it predicts, it takes, or as it did the chemistry prediction, I feed that back in for the physics prediction, then I feed it back in for the materials prediction. So as it predicts, you're feeding that same, so it's getting more and more information each time, so it can refine more and more and more each query. I mean, it makes like probably 150 queries for material, it takes about 40 minutes to analyze the material. Because I'm trying to like make it force feedback the information in the system, so the prompt gets more complex over time, so its analysis gets more complex over time. So it gets more accurate, more accurate, more accurate, the more prompts you feed it, right? Because it has more information now to go on, and then you have to reanalyze at the end on whether it thinks it's right or not. So that's kind of like the control steer I'm trying to do to keep it as accurate as possible. But it does need people to go actually make the material and feed the information back in, so that it gets smarter, right? But the intention is to reduce the time it takes you to come up with a composition. Right, because no one can be a physicist, chemist, or material scientist all the same person and know the entire corpus of knowledge. So the point is, it's not that it's gonna just automatically make these new materials, it's gonna give you a starting point to go synthesize and try and reduce the trial and error time. That's the whole intention of it.
How many people have you got actually building stuff out of this?
I just the first group I've ever presented.
Oh,
Yeah,
okay.
Or you can use it for your project.
I'm using it for my project, yeah.
Yeah.
I did, but,
So you'll be your first test case.
yeah, I'm already using it for that side, yeah. I have the prototypes on my desk right now, I've been testing, so.
So you've created the materials.
Some, yeah, for the graphic concrete. So like what other things I could add into it essentially to make it better?
How's that working?
Good, actually, yeah. It's about 4 times the density of lithium ion per kilogram. It's concrete, so I can pour the foundation of a tower out of concrete and store 4 times the density of a lithium ion battery. And there's a lot more concrete than a battery. So,
If you took a novel material
Mhm.
and put its structure into here, would it tell you what the performance would look like?
I
I
can
think
try.
it would be.
it should be able to,
That actually is a pretty powerful use, because a lot of people try to create things.
yeah. I'm gonna make notes about these things and add those features, 'cause I like that one too, like taking basically known materials and what its performance would be. And then simulating materials that were predicted after a certain time, cause you can tell GPT that and it'll do it. I like that idea. Any other questions?
Actually, that would validate part of your model too.
Yeah,
Yeah.
and then I can use that validation to make itself smarter. So I can then take the validation of whether it was correct or not, and then feed it back in and say, you were off here, go analyze why you were wrong.
But would that material already be in the corpus that it's analyzing?
It would, but
Doing a comparison of 4 years, like, because you said that the corpus includes studies.
you can discard the information before a certain date. Right, so you can make it not find the information in the data by saying, don't look at stuff before, or after this date. And so then it would analyze it based on the information before that date, and then you can feed that analysis back into what was actually predicted and take the difference and then feed that back into your learning model. So that's a really great suggestion, think about that.
Also, there are a lot of novel materials that haven't been characterized yet, so it'd be nice to be able to predict what they're gonna do.
Yeah, that's a great idea.
And we run into a lot of them that are built for one thing, but then because when they get characterized, you go, whoa, this is good for something else.
Right.
So
If you can send me a list of materials, I'll run it on it for you and send you the reports.
I know some people that can do that.
Perfect.
Woohoo.
So yeah, and then following up on the demo here before we're running out of time, when you analyze material, it gets saved down here in the analyze materials, and then materials you like, you can save them, so you don't have to filter through the entire set of data for materials you wanna try to create. So I've analyzed these, identified, well, this one is older, so every data stuff, my bad, but so I wanna create this material, so then I go and try to create this one, because I saved it in my save. So it's just a way of organizing materials you wanna try to create and synthesize versus just looking at this entire list, which is thousands of materials at this point. And if you let it run for multiple days, you have hundreds of thousands of materials essentially. But 1,000 every 20 minutes, so you can do the calculation to figure out how quickly it's gonna scale data wise. So that's pretty much it. I mean, it just sits there and predicts materials, generates properties, and they analyze them, and then you go make them in a lab to see if it was right, essentially. But I like the two suggestions. I'm really gonna go home and implement those. If I can actually make a train better. So that's the demo. The team right now is just me. I'm looking for additional people to join. Chemists, physicists, material scientists, additional computer scientists that wanna take it. I mean, I'm a very busy person in multiple companies, so I need people to help, progress the project. And really, summary again, I'm just trying to reduce the time it takes to make new materials. Like when I was doing graphite battery, it takes a lot of time to find new things, make the battery, try to figure out what it's gonna do. And I was using the system originally to try to help predict that. And I thought, well, maybe we can use it on a broader scale. So it's not that it's gonna accurately predict all the materials you can make, it's just to reduce the time it takes to find new materials that meet the properties you desire. It's extremely performant, doesn't require large supercomputers like every other version that's doing like DFT simulations to predicting materials like Microsoft and Google. It's practically utility. So if there's no more questions, there's a lot of questions. Is there any more questions?
Mine a little fast.
I know.
This might be a little fast.
We had 30 minutes, so I was trying to fit it in.
Material, it's like, is foam a material? Is a sponge, like,
Mhm.
Are the macro and mesostructures part of the description? Or, cause I see chemical formulas.
Yeah.
But the same chemical formula can take many different forms
Right.
depending on how
This is true.
it's made, and so. Yeah,
I haven't added that, but I can add that definitely. Can you send me your feedback to anyone about
I
that?
don't know if I can, I probably won't remember it.
Jot it down now.
No, like,
The video is recording.
Well, yeah, it would be a recording give you.
Oh, I can go back to that, yeah.
There's AI and everything, but, I think, yeah, the interesting thing would be, like, yeah, form and, application, I assume is part, you got your example of your own application and having a, versus of, I need a material to do this, but what is it you're doing? The thing is, oh, I'm making a robot, or I'm growing a tree,
Okay, yeah.
or whatever it is, maybe that piece in there can drag the form towards the material in the form. perhaps.
So more than just properties, but like the actual desired outcome
Yeah.
to help drive the more narrow prediction.
Mhm.
That's a great idea, because I'm doing anything for, I'm doing potential applications, but nothing with form yet to answer your question. So,
well, sorry, I really am not quite grasping it all. So, for example, I want to generate silly putty.
Mhm.
How do I describe silly putty in such a way that this will get generated? Right, so it's one thing, you have these descriptors or properties that you can specify, and they went by too fast on that. But could I describe silly putty or, egg white?
yes, so there, you can type anything you want in the box. And it'll try to give you the properties that would give you that.
Egg white's a great example of what you're talking about, because it's kind of boring when you just put it on the table here, but if I whip it up,
Exactly.
I get something completely different.
No,
But the chemical composition is
it's
identical,
exactly the same.
Right.
yeah, so you couldn't tell from chemical composition.
How the form will
That's what
change.
I've got.
Yeah,
That makes sense.
I get you.
Yeah, I'll add something to see if we can predict that. I'm not sure personally. But
Really shows up with carbon.
Hmm.
It really shows up with carbon.
Right.
It's like,
I don't know.
it's incredible range of things depending
From
on,
diamond to.
yeah.
Oh, you got a point there. Be a very large range,
Yeah.
graphene.
Lucky balls. So let's say you're successful and this thing starts getting really smart and it becomes really, really valuable. Is it an open source tool for everybody in the world? Does it generate investment and profits and companies? Do you seed it to the Atlas Institute and let them raise a bunch of money? What's your vision? Where's it going?
I want it to be a collaborative open source project, but the company itself will get a percentage of patent revenue. Small, very small percentage of patent revenue for any material that's made.
So it'll be built by a company that's invested in and licensed out for its use?
Yeah, but it's open collaboration.
Okay.
So anybody can join and help the project and produce it, but the company still has to make money, right? Cause you still have to run the infrastructure, you still have to, things are expensive to run at scale.
Okay.
So taking a small percentage of patent revenue is not a big ask. Like 1% of patent revenue is not a lot of money for people. And then it's, whenever it's actually useful to people, that's when you're getting paid, but before it's useful, you're not making any money, right? So it's a way of making it open source so anybody can use it without requiring upfront payments. Or any money, essentially, and everybody can collaboratively add to it. There's a lot of smarter people than me in the world. I'm one person. And I'm open to inputs on that too, because it's still.
Well, it might be good just to have an example of a similar corporate structure that reflects what you want to do, whether it's, you know, some like OpenAI or something like, you know, like a farmer's co-op or whatever it is, you know, model that same structure.
It would probably be more like the Kubernetes Foundation,
What?
Kubernetes Foundation,
Okay.
very similar to that. Cause it's an open collaborative project where like everyone joins as collaborators and builds the product.
So could you, put on the screen the URL for going to the product, cause you went through that quickly. and-
Yeah, sorry, we only have 30 minutes, so I was just trying to get through everything. So it's just synthaiproject.com. And it goes into more detail too, like a lot of what the slides went into, if you come here and you click how the platform works, it goes into pretty good detail with diagrams and on how the machine learning works, what libraries it uses, how the libraries work, what it's predicting. I have a talk in here about what GPT-5 can do again, so you can further see like why it's being used, how it's used, why it's valuable, some of the performance indicators of GPT-5 as it relates to like scientific inquiry. It kind of goes in like detail of like how it works and why it makes sense. Because obviously we have 30 minutes and that's the day, and it's a very complex thing.
How hard is it to repeat what you've done?
I mean, a person that had relatively good programming skills and a basic understanding of science probably could do it. Maybe. It took me a while, but I mean, any software can be replicated, right? If you know how it functions. So, if you're a competent programmer and you know anything about science and the libraries used and how they're being used, you can probably do it, especially with like AI tools today, like Cursor or GPT-5.
And it just time, takes time to.
It does take time, yeah.
Intelligence.
Is that what you answered? Pretty similar, the response.
Well, that's a good question too, but for me, it's more like if, you know, your business model is a back end 1%, which 1% is actually a lot, and you know, when you're asking. And is there something else you could do, like if it's a viable material, do you, you know, prosecute the patent and, you know, you take care of those, you know, what is it that the company does beyond, hey, I just did 3 months of work.
Yeah.
You know, in order to get that kind of a back end on something.
Running the infrastructure.
What's that?
Running the infrastructure, because you have to pay employees, you have to pay infrastructure at scale.
Yeah, I get all that, but it's more of the value proposition, what you're offering to those that are going to use it.
Yeah,
But then after 3 months, figure out, oh, I'm gonna hire this group of 5, you know, and
true.
in 3 months I have it.
Yeah, I mean,
In order to protect what you have.
that's at the point now, right? But as people join the project, as people help develop expert, you know, chemists, scientists come on board to help refine it, it becomes a different story. You can't just go rebuild it with programming. Right, like it's at the point now where programming is almost at my ability limit as a programmer, and I know some science, but I'm not a professor in chemistry, you know, or physics or material science. So that expert knowledge that joins the project and adds their value to it, that's where the value prop is, right? Refining how it analyzes things, refining how it produces them. That's the knowledge base that you can't replicate as a programmer. So that
Basically a stone soup.
basically, yeah. I mean, if you get a collaborative group of professors from all around the world and computer scientists making the model better, you can't replicate that. You couldn't afford to replicate it unless you're Meta, right? They're paying $1 billion for AI, but that's the kind of the intent here, is the value is getting a group of people to get their inputs, refine it, and make it better over time. Because that's a lot of value. Like, I think we really can reduce the material creation time by 10x, like the world would change. If we produce a room temperature superconductor, that would change our civilization. Under ambient pressure, like we'd be a type 1 civilization in 2 years if we could do that. So that's the intention here, right? Like, how can we predict materials that might give us what we need, and then to reduce that time, so it doesn't take us 20 years to make a new material, and make it industrial viable.
Who else is working on this?
Just me right now.
I mean, I don't mean on this project, but who are your competitors?
Google and Microsoft. but they're using advanced supercomputers and DFT, so it's not available to
And the
everyone.
whole pharmaceutical world,
Yeah, the pharmaceutical is doing,
that's where the money is.
AI-based molecular combination, yeah. I watched the video the
Not
other
the
day.
first time I've heard this one.
There's a group doing quantum computers to do it too, to predict, medication inputs on the human body and what the results will be.
There's also a lot of interest in the, what's the process, manufacturing for chemistry, because it's a tweakable system and you'd like to be able to predict what comes out as you tweak the process, so they're using a similar approach. Bunch of those companies are going after this pretty hard.
It just seems like our presentation is more of a corporate speak style, and what you're really trying to get is an altruistic
Maybe.
joining kind of thing.
Yeah.
And so maybe that vibe needs to tweak somehow to get what you want, which is you want people to join in and cooperate, but you also want to, use some kind of altruistic purpose to get that going.
Yeah.
And then, you have to have a back end, you have to have something that's gonna fund it. But this feels more like the pharmaceutical thing versus the I don't know, Ubuntu kind of thing,
That's a good input. My interest is just creating new materials. I just want to create new things, so.
Yeah.
That's my overall interest with this platform,
Right.
to get people to help create new materials and things so we can change society. By reducing the time and cost to do it. Cause like, why do, why is it such a large, or why does it cost so much money and things end up being so expensive? Because it costs money, right? To build a material, you gotta get investment. If you get investment, you need to pay that investment back to someone. So there's always a corporate interest in developing new material.
Sure.
But if you make it more of a collaborative effort where it's less about the corporate interest, you reduce the cost, more and more people that don't have $1 million labs could then go and make that material and go and do that thing where. Like me at my house, like I have a lab, I have a shop, I do things in, but I don't have like electron microscope, for example, right? I can't look at like the structural lattice of what I make. So like helping like predict those things so I don't need that equipment will help me it helps me make more materials quicker. At home.
If you get back to like something like the SETI project, well, let's look at all this data, little chunks of data. And see if there's aliens out there, that's cool, but if you have I'm just wondering. Is it somebody experimenting with a material or taking one of your recipes and doing something with it, feeding back in, or is it trying to raise the money to do that?
I mean, some of just experimenting. So like I'm a chemist at a university and I'm trying to make new material, right?
Okay.
Instead of trial and error for 10 years, I use this to find something that might work and I reduce my trial and error time by 10 factor, right? So it takes me 3 months to a year and a half versus 10 years to make a new material. But that's the intention, right? Or be at home, like I'm trying to predict new materials for my concrete batteries or to make better batteries, right? For my project. So it helps me reduce time and figuring out what I need to target for that, if that makes sense. So it's not necessarily that you go raise money for it, it's more like someone who's already trying to create materials and they're using it to narrow their search scope is the best way to look at it. It doesn't give you exactly what you make, it just narrows your scope. And it uses information from multiple disciplines to help you understand what it could be, not what it is, right? There's no way to really truly predict at our current level like what it's actually gonna be. It's more of like a starting point, so you have a good understanding of what you should expect. And then as people feed the information back in, it'll get smarter and better at that. And the 2 suggestions you guys made will actually help me make it smarter. So I'll put those in, I'll just have it run in the background. And keep simulating different known materials or novel materials that haven't been predicted, and then keep learning from that. Even outside of someone going and making the materials that it's predicting, so I can use that information to feed into the learning system to make it smarter. Cause I want people to make new materials, that's all I want, that's all I really care about.
Can I ask a question?
Absolutely.
Hi. Hello. So all your system is based on ChatGPT 5 or you have other model to
No,
help?
so the initial generation of predictions are based on PyMatGen, and I'll go back to the slides easier. Or PyMatGen, SPGlib, ASC, and MapMiner, and MapMiner is from like the Open Materials Project. So the initial generation of predictions are based on those 4 libraries, which are already used in this type of science. GBT is just used to take those predictions and analyze it further. Because they only give you like properties, essentially, right? It's not gonna tell you what it's gonna do or how it should be. If you're a person like me who's not a scientist, like I may not know what band gap is, right? So by analyzing the material, I can look at the properties and send it into GPT, and then now I can look at it from an expert chemist perspective, an expert physicist perspective, an expert material science perspective, and kind of understand what it should be, right? Because like no one can know all that knowledge. Like if I'm a physicist, I might not know the chemistry side. From material science, I may not know in-depth physics, right? So like having that ability to analyze the things that I don't know gives me a better understanding. Then I go look it up too, right? So like, it's not just I trust it. I can go, oh, this means this. Let's go look it up and understand it further. So it gives you like focus points to go learn knowledge that you might not know as well. So it's trying
But
to,
but those model or even ChatGPT, I mean, this is really old school LLM question. How do you deal with the hallucinations? Yeah,
absolutely.
even you got a reference, sometimes you click into the DOI, it's wrong. Yeah. So how do you deal with that?
Absolutely. So, if you look at the current like performance GPT-5, it's 98 to 99% accurate in scientific inquiry.
No, it's not. I tried.
Did you? That's the stats they released. But the point is like humans aren't correct all the time either, right? It's not intending to be like this is 100% accurate. It's meant to be a starting point for you to validate whether it's accurate to make the system.
Yes.
Yeah.
Actually, yeah, so okay, I will tell you that because I'm using the ChatGPT 5 now to writing code for my mixed reality applications. Even I give really restrict prompt, it's still hallucinated every time. So I would say LLM still have that kind of problem. So either you have to justify like how do you avoid that, or to tell people like that's not the accurate information. That's one thing. And the second thing is how do you retrain your model? Actually, you're not really talking about that because when we talk about retraining the model, it's like changing the weight or changing the model weight, but something like that. But we cannot change any weight of the ChatGPT 5. So
We're not retraining
yeah.
GPT-5, we're retraining XGBoost and IGBM. We're not retraining the LLM. We're using the LLM for analysis. The retraining happens on XGBoost, IGBM.
Yeah, depends on what kind of the data you're doing the retrain.
So I guess along that line, have you asked repeatedly, this is what I want as an output? Because you will get different responses. Have you done that?
Yeah, I mean, I tested quite a bit on that, and it specifically has to do with the way you query and what you query, right? If you make your query really broad, a lot of times it'll hallucinate. If you make your query, I use GPT and AI a lot, so if you use, you narrow your query band, it's more accurate more times, right? And it depends on what you're asking, like with coding, it'll hallucinate more than scientific inquiry. Because the coding is creating something. Scientific inquiry, you have to understand LMs work. They work on vectorizing text databases in natural language. So if you ask it to create code, it's creating something based on what you're inputting. If you ask it to analyze a body of text, it's not creating anything, it's returning an analysis based on a body of text that it knows. That's why with scientific inquiry, it's actually a little bit more accurate than it is with coding, or like, I want you to write an email for me that says X, right? Then it's creating something again versus analyzing a body of text. If you take like Socrates, for example, and you put it in and tell it to analyze it, or give you a specific passage from it, it's gonna be able to do that without hallucinating. So the
That's
same.
my question.
Yeah.
Have you made the same identical inquiry 100 times?
Yeah, because I rerun the analysis multiple times,
Yeah, you're
and it
asking-
resets the data.
You're asking to separate between different types of accuracy, right? So repeatability versus, so scientific databases work better if you're measuring the accuracy of the combinatorial effect because there are less lies, there's less information, so you get a better result. But you don't necessarily, that's not telling you anything about repeatability.
Yeah, so when I analyze the material, I hit reanalyze like 10 times, right? Like I analyze it over and over and over again, and I see how the data changes with each analysis. And in the beginning, it would change a lot. Now it's pretty consistent between analysis. Like it almost never changes now between analysis. It does change a little bit in certain things, right? So as I keep refining like how it's making those queries, it's not just asking one big query like analyze this whole thing again. It's saying here's property one, analyze what it's gonna do. Here's all these properties, analyze what it's gonna do. And it keeps feeding that information back in, trying to get it to remove the hallucinations based on the increasing prompts of queries, right? So It's not just asking it one time for a query, it's asking multiple times, making multiple different prompts with increasing knowledge base as it goes through it to try to refine it. It's not gonna be perfect, no, 100% not.
But you're feeding it its own answer.
Yes.
Which is different than.
And then asking it to refine its answer based on the new information. They give me this information based on the old information to refine. And then look at the sources that you're using for that information. So every time it's not just making stuff up, it's trying to find the scientific paper or the theoretical assumption based on known science to make that analysis, right? So that's how I'm trying to reduce the hallucinations. And again, nothing's ever gonna be perfect, especially with AI, until maybe we get to AGI, but it's not gonna be perfect. But the more we can refine that process too, like having a chemist come on board, if it's material science, and tell me this is wrong. I can then refine the query so that it hallucinates less. It's never gonna be perfect. But it's better with already knowledge it knows versus coming up with new knowledge. So that's why I try to prompt it in that way. I don't try to tell it to create new things. I try to tell it to look at existing knowledge and tell me how it thinks it should behave versus write me this code.
But isn't the value in coming up with novel materials?
It is, but based on known science. You don't want it to try to just come up with its own stuff. You wanna see like, what do you know about how atoms bond in this way? What's the behavior? And then this is my properties of my molecule. How do you think it's gonna behave based on that knowledge? Not come up with some new science and how you think it's gonna behave, because then there would be hallucinations all the time. Right, so you're trying to use established information to make the predictions rather than come up with new information. That's how it's prompted. Is perfect? No, absolutely not. But can it get better over time? Yes. The more you change your prompts and the way you're prompting, it can get more accurate over time. And I've played a lot with this with GPT, especially in coding, because I use it a lot in my day job. So like how you specifically ask the question and what you tell it to give you will dramatically affect the hallucinations. Because the other day I was using it to build a backend server for a game, for example. And I had an cursor agentically write it and solve its own hallucinations based on my prompt. So the same way, like I'm using that similar logic to try to solve the hallucinations of its analysis. But that's why you physicists, chemists, and material science to come in and validate what it's doing and tell me where it's wrong. Because my knowledge is limited in some respects in that regard, so can't do it. There's probably additional AI and additional models we can add to it to make it more smart too, and train our own LLMs. I went with GPT-5 first because how many billions of dollars have they spent building GPT-5 and training it? And they're building nuclear power centers now to train. I don't have that much money to train a new LLM.
Which you can ride on.
Yeah, but we could take GPT's analysis, feed it into a bedrock LLM and create our own that way. So like you can create your own LLM to get smarter over time based on GPT-5's analysis.
Is there a better way to get to the more accurate answers quicker? So I was thinking of where the real value, where a lot of short-term value would be finding new applications for existing materials.
Yeah.
Right, people that already make something, you give them the ability to sell it into a new market. Could you tweak this engine to be able to say, hey, I'm gonna take the product line of this chemical company and give them a whole bunch of new uses for it because on the other, you're doing it on the other way, you're saying, I've got a use, now I want a new material to satisfy that use. Could you reverse it? And it might generate a lot more short-term income to run your company.
Yeah, and it'll be a lot more accurate too, because it has the known data on the material.
Right, I mean, the big challenge that for me in watching this was, you started out saying, well, I don't even know how the atoms bond together, right? And I'm like, how can you do accurate projections from the thing that you don't even understand how?
Let the libraries do it.
But if you started with something where all that's known, and then now work it backwards and get it very accurate, now could you reverse the model?
Yeah, that would absolutely work. You could do that. It'd be a lot easier to do than trying to break new.
And the results would be pretty valuable.
Yes, it'd be more accurate too. Because again, it's based on known behaviors versus trying to interpret what behaviors might be.
You got lots and lots of unknowns in this model
You
right
do,
now.
yes, absolutely.
That's hard.
100%. But again, it's not intended to be accurate. It's intended to give you a starting point.
No, you gotta have something real at the end.
Yeah.
When did you start working on this?
I've been ultimately developing this for about 5 months.
Okay.
I started building the code within the last 3 or 4 weeks, but I've been designing the system for a while since I've been doing the graphic concrete. Yeah,
Relatively new.
super good. That's why I'm looking for people to come in and help validate it. And give me this feedback. This is really great feedback. It's gonna help me to really drive some changes in how it predicts things.
Well, this is a little tongue in cheek, but if I'm an investor in your concrete company, I'm saying, stop doing this.
That was something I wasn't gonna bring up, but the intellectual property side of this is a big deal. how you handle these databases, that's the thing.
Well, the concrete, we're already gonna be using in our telecom project.
It's very tongue in cheek, but
Yeah.
focuses everything, right?
Well, it's not really. As soon as you create the first truly valuable thing out of
Yeah.
it, somebody's gonna.
Well,
want to
and,
hold it down.
and two, it's like, this is the sort of thing, it's like being on Instagram, an hour just went by, how did that happen? You know, the same thing, I can see that being that same feel
Yeah.
versus, oh, this concrete project, I got really hard ditch digging to do here, and I don't wanna do that.
My key,
Anyway, you know all about that.
oh yeah, I don't sleep. I organize my day into a series of tasks every day. But the concrete stuff is like my fun project. I've been working with graphene for a while. I really like its applications and potential use cases, so it's a crazy material. Any other questions and feedback? This is really good stuff.
Interesting.
I can really make it a lot smarter based on you guys' feedback, especially with like what you guys mentioned with testing novel materials and trying to predict if current materials have been made that predict the same properties. That's a really great idea. Any others?
Although, no, I don't have anything more, but since Ellen has left the room, I'll take it on myself to wrap this as the first. Thank you, inaugural fall 2025 academic year colloquium. Great start.
Yeah.
You set a high bar for the rest of us to. But thank you for this, and this is, I like to call this Ellen's Eclectic Experts, because this is, the next one I'm sure will be totally different. She collects the most interesting, diverse group of people, so the next one will not be like this, it'll be exceptional in its own way. Ellen's Exceptional Eclectic Experts for you. Thanks, Grant.
Thank you. Appreciate you guys.